How is everybody? Braden, Cody, Alec, Brandon, Glenn, welcome. Good to see you.
How are you doing, Brother Smith?
Doing great. It's Friday. You guys have any good plans for the weekend?
Not yet.
Oh, let's see. Is everybody married? Braden, are you married? Oh, Braden's married, Brandon's married, Glenn's married, Cody's married, Alec's engaged. You guys aren't going to be going on any new dates this weekend, but you can take your wives or your fiancés out. Maury, welcome. Renata, welcome. Okay, let's get started. Welcome to class today. Good to see everybody. Let us start with the prayer. Alec, could you offer us a prayer this morning?
Sure can.
Sir.
Dear Heavenly Father, we're so very grateful for this day and for all of our many blessings and for the chance that we have to be at this school and to be in Brother Smith's class today. And we're thankful for all his preparation and all the work that he does to teach us these concepts that we can one day take them into our careers and to be able to enrich the lives of those around us. And we're grateful for our Lord and Savior Jesus Christ, who died to allow us to be better each and every day. And we say these things in his name, even Jesus Christ. Amen.
Amen. Thank you. Appreciate that. All right. Well, piles. We've been talking about piles for a while, and I want to just pause and ask you, what have you learned so far? What do you know? Teach me something you've learned about piles.
I never knew that piles could be over 60 feet long. I think that's pretty incredible.
What do you think the longest pile ever has driven has been?
That's a good question. I would say 200 feet.
Does anyone else have any guesses? I was very surprised when I found this out the other day. Over 700 feet. That's crazy. That is crazy. So, wow, don't know how they did that. I don't know why they did that. That's probably very expensive, but maybe they're just trying to set the world record. It was like 760. Who knows? It could have been more than that, but impressive. Piles are deep, super deep. Sometimes they go down all the way to some hard layer. Sometimes they're just hanging out in soft layer, and they're dependent on that friction. All right, what else have you learned about piles so far? Teach me.
They come in a lot of different shapes.
Shapes, sizes, materials. Yeah, surprising. Wood. Did you know wood piles can last for like ever underground in like a water saturated condition? That's just crazy, forever. However, piles in the ocean, they don't last forever. Why? Because there's biology in the ocean. Microorganisms eat away at it. But if you have a pile buried in soil, in the ground, in water, it lasts forever. I don't know why. Maybe there's just way less organisms that eat away at it. But they've uncovered piles thousands year old that were buried in the ground, and they look really good. So, of course, you can now chemically treat piles to help them last a little bit longer, but I was just shocked. Piles in the air, piles in the ocean water, or piles in the ground in groundwater. They all behave a little bit differently if they're timber, made out of timber.
I think this might be jumping to conclusions, but isn't that how wood is petrified in the first place? Is it's
Hey,
buried
there you
under
go.
water and clay?
Yeah. I was actually, when I lived in Arizona, we went to that petrified wood forest and it was amazing. You could see all the little bark shapes on the pieces of wood, the rings in there. Yeah. So for millions of years, it was preserved. And then slowly, as the different minerals ran through it, they replaced the wood with minerals and they left a rock. Looks like wood. My son actually took up pieces and put them in his rock tumbler and polished them up. And they look pretty cool. All right. What else have you learned about piles so far? Teach me something, anything. What have you learned about piles? What's pile capacity, pile sizes, shapes, whatever. I need some feedback.
There's basically just two factors that we account for the how much a pile can hold, and that's the load the point can take and then the side friction load.
That's right. So piles, pretty basic. A pile can hold whatever it's bearing on and added with the side friction. Some piles only have tip resistance because the side friction is negligible. Some have only friction on the sides because they don't bear on anything meaningful. Some have a combination of both. I like that. What else have you learned?
You can build wherever you want with piles.
Holy cow, yeah, you can build in the middle of the ocean an oil platform with a giant pile hundreds of feet deep, going through 100 or 200 feet of water, bearing into some muck, the ocean bottom. That's a pile. Huge piles. Yeah, you can build anywhere. Holy moly. All right, what else have you learned?
I didn't
Teach me.
realize I didn't realize that sometimes when they have a really long pile, they connect them or weld them there on site.
Yeah, how cool is that? You can keep going and going and going. I mean, that's how they probably got to that 700 plus foot pile. They just kept welding on, going, 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 driving it in. What are the different ways that you can drive piles in? What do you know?
I think there's the hammer, and I can't remember if it's like a steam method. That's what they called it.
Mm-hmm. Yeah, back in the day, they had to use steam engines and bang it down with steam. Now they have diesel hammers. Does anyone know how a diesel engine works? Tell us how a diesel engine works, Adam.
Well, it's only a little bit different than a gas engine. You compress diesel fuel to a point of combustion, and the pressure gets so high, the temperatures rise, and it explodes. And you have a chamber, and that explosion pushes a piston down, which turns a shaft. And
Okay.
basically just repeat that process over and over.
Yeah, but there's no spark, right? It's this, you inject gas into a cylinder and you compress that cylinder so much, the pressure gets so high, the heat rises until it hits the ignition of that diesel and it just explodes that piston out. No spark needed, just pressure. Well, a diesel hammer works the same way. You have a giant chamber, you raise a piston up in it, squirt a little diesel in, and then you drop that piston and boom, it falls down, it compresses so much that it fires it back up. They squirt a little more. And if you just put that up on top of a pile, the only thing you need to start with is lift that heavy, heavy piston first and then drop it the very first time. And then boom, you started this process. As long as you keep squirting in diesel every time it falls, that's what a pile hammer is. It's just, and they're heavy, they're massive, and just the weight of them. And so depending on where you're at, you order a different size of a diesel hammer or a driver. So that's good. There's also vibratory hammers as well that can vibrate them into the ground. All right, what else have we learned about?
You can cast them in place if they're concrete.
Ooh, yeah, we can cast them in place. We don't have to bring it to the site. Maybe you're in a difficult location and getting piles in and out. Maybe you're on an island, who knows? You can cast a pile, lift it up, and drive a concrete pile into the ground. We're also going to talk about auger cast piles next week. So, okay. Let's learn a little bit more about piles today, but let me share my screen. Can you see that? Okay, so pile foundations, pile driving. So we've been talking a lot about how to figure out the bearing capacity, and hopefully bearing capacity of piles remind you of chapter 3 when we talked about Terzaghi. Actually, let me stop this. Oh, look at this equation right here. Can you guys see this equation right here? Get that. This is one of my favorite equations. This is like from the father of soil mechanics. If you're going to geotechnical engineering, this should be your favorite equation. It tells you how much soil can bear, how much it can hold. It's made of 3 terms. It's Terzaghi's bearing capacity equation. It has a cohesion term, a surcharge term, and a foundation soil weight term. And each term, C is cohesion, but then each of these, N sub C, N sub Q, N gamma, that all, you know, everyone decided after Terzaghi invented this to add their own. And so you can, there's tables, there's ways, and you can figure this out. If you're just dealing with sand, of course, the cohesion term goes away. BF, that's kind of the footing width. When it comes to piles, we use this equation, but we don't use all 3 components of it. If we're in sand, we knock out this cohesion one. And because the base of our footing is so tiny, it's just the diameter of the shaft, maybe 1 foot, maybe 2 foot. You can go up to 10 feet, but that's a big pile. We ignore this component. And so essentially it's just Q, the surcharge, times some modification factor. And surcharge, again, that's just the unit weight of the soil times how deep it is into the ground. So the deeper you go in the ground, the more that soil's pressed together, it's tighter, and it can hold more load just because it's deep in the ground. So anyway, I can't say enough about, these are the fundamentals, because when you're taking design classes, the point is not to memorize a lot of equations. The point is to understand theory. And so this is soil theory 101 right here, Terzaghi's bearing capacity equation, and that the 3 pieces that go into it. And a pile, walls, shallow foundations, deep foundations, bearing capacity, settlement, slope failure, it all hinges on these soil 101 concepts that were kind of put together by Terzaghi. So, okay. Oh, dang. I covered the picture I really wanted to show. This. Okay, we've been talking about bearing capacity of piles, skin friction of piles. I just wanted to show this table right here because I found it was a good summary. I mean, last time we talked about 12 different ways to calculate skin friction and 5 different ways to calculate bearing capacity of a pile. And here was just kind of a good summary. If you're trying to find this NQ, the surcharge factor right here, here's a couple different authors, Meyerhoff, Hansen, who knows how to pronounce that, Terzaghi. And you just start with this table, you know the soil friction angle, and then you pop up, and then you come over and you can figure out this NQ factor right here. And who do you use? I don't know, but here's a good range. This is a range suggested for design. If you're a good engineer, you probably will not pop outside of this range right here. So while there are many authors who have suggested these bearing capacity factors, if you stay within this range, you know, if your N sub Q factors, you know, based on your friction angle, stays right around these ranges, you'll be safe. And anyway, just wanted to share that with you. There's more foundation books than the one we're sharing. There's probably 10 different foundation. I was talking to my buddy who was working on his PhD in Virginia Tech. And I was like, share me your notes about soil foundation. And he had his book and his notes, and I was reading that. And it does, none of his equations match the equations in our book. We have this book. It was written by, who's the author? Doss. He writes a lot of books. I mean, these are this. I mean, it's kind of like Moroni. He abridged all these plates. He had so many plates, and he had to choose the best. He saw our day, and then he picked the best pieces that would match the times that we were going to deal with. And Moroni and Mormon, they abridged all the plates. Well, that's what all these different authors do. Doss, he abridged, and he found his favorite equations for calculating pile capacities or whatever. And then another book, he'll pull in his favorites. Anyway, there's lots out there. That's the whole point. But what doesn't change is the theory. So the theory behind bearing capacity is it follows Terzagh's equation. And what's the theory behind skin friction capacity of a pile? What are the three components that make that up? Who knows? Garrett, I'm calling on you out of the blue. Skin friction. What do you need to know to figure out skin friction? There's three general things you need to understand. Two about the pile, one about the soil. What are they?
There's the perimeter of the pile.
Yep, got to know the perimeter.
Length.
The length of the pile.
Length. Oh, and then, friction factor.
Boom, friction factor. So that's the theory. You need to understand that. Now, friction factor, I mean, there's a million ways to figure that out. And the site condition that you're in can help you figure that out. And you may not know. And so what you may need to do is you may need to go out into the field and actually investigate this with a test pile or something like that. So today we're going to talk a little bit more about how you can go out into the field and calculate the capacity of a pile based on in-field pile driving conditions. And we're going to talk about, well, what happens when you have multiple piles and how you have a group, what's going on. But before we start, I don't want to take the time to bring up iClicker. So I want you guys to just look at this and tell me in the chat, what is the equation for work from physics? What do you remember work as? What's work? Throw it up in the chat. See what you guys got. A, B, C, or D. Getting a couple B's, lots of B's. Everyone's saying B. Okay, who would want to say anything else but B? Okay, I got it. You guys understand work. That is correct. Work is force times displacement. So if you're a hammer and you hit a nail, the force hitting that nail drives, or the force of the hammer drives the nail in a certain distance. Well, good geotechnical engineers took this same concept out into the field, and they thought, if you're driving a pile in the ground, that's like work. That's like hitting a hammer or hitting a nail with a hammer. We could calculate how much work, and maybe we can back calculate work into some ultimate bearing capacity of the pile. So if you're not comfortable using all these equations in the book, calculating your ultimate bearing capacity of your pile based off skin friction and end friction, what could you do? Well, you can go out in the field. And so sometimes your calculations, okay, I need to drive this pile 46 feet and it will be just right. But sometimes when you get to 46 feet, you don't have the capacity. For whatever reason, your soil conditions were not what you thought they were. They may have changed, that you may have not had enough laboratory tests to adequately characterize or classify the soil conditions. Anyway, you're at a depth 46 feet, but you don't have capacity. It's just going in the ground. It's just acting too soft. And so they wanted a method out there. So if you got to the depth you think you needed, but weren't seeing the kinds of blow counts or still driving in too easily, you could keep driving the pile and then weld onto it until you got to a depth where it was so dense that it was barely being driven into the ground by the hammer. And so there's equations that have been developed to determine the ultimate capacity of a pile during driving. So no calculations. This is purely field observations. And so ENR, Engineering News Record, has a formula, and it's all based on the work formula. This should look familiar. Work equals force times distance. Well, they kind of said energy from the hammer equals pile resistance times depth of embedment. So they kind of modified this equation. They did a little bit more tweaking with it, and they said the ultimate capacity of a pile equals the weight of that huge ram times how many feet it's dropping divided by the penetration per blow. So if you imagine, if you tap on that pile and it goes down 1 foot per blow, that's probably pretty soft. But if you tap on that pile and it only goes down like 1 inch each blow, that's probably pretty dense. And so S is the penetration, and then C is a constant, and it just allows you to jump from metric to English units. And so if you're doing, oh no, sorry, C is a constant, not at all based on that. I thought it was, but maybe it still is. But it's saying drop hammers use 1, steam hammers use 0.1. I still think it has something to do with metric in US. But anyway, then after all that's done, you can apply this whopping factor of safety of 6 to your Q ultimate, and that will be your Q allowable. So when you start seeing factor safeties of 6, that just tells you that engineers are, in the military, they call it rear guard action. They're protecting themselves from future litigation. So factor of safety of 6 is what you divide this by. But you're able to now kind of figure out penetration per blow, and you can kind of rearrange this equation even more. And anyway, this formula has been modified many times, but it's all kind of based on that formula of work. And so what it allows you to do is, and I've done this before, one of my first jobs as an EIT was to go out in the field. We were working by the Salt Lake City airport, which was based on old ancient Lake Bonneville. And so it's a lake bottom bed with a bunch of silts and clays and a high water table. And the company was Lockheed Air. Maybe you've seen them. They just suck air out of, they take air and they break it down to its components. And so they make liquid nitrogen, they make oxygen, and they make helium and all these other things. But these huge tanks that they stored this condensed air in, all these tanks were on piles, bunches of piles all tied together. And so my job was to go out there and watch these 50 to 60 foot piles get driven into the ground. And my job was to keep recording to write down on a log how many blows it took to go each foot. So at the top, one blow went like 1 or 2 feet. I was like, whoa, this is tough. As soon as it started getting deeper, it was taking like 50 blows to go a foot. And so we were getting some really dense sands down there. And then we said, okay, you can cut it off. And so the engineers had come up with this, used these bearing capacity equations and said, if you're at these many blows per foot, you can stop. That pile has adequate bearing capacity to go on to the next one. And so we did dozens of these. There were so many piles, they're driven them all on the ground. And so anyway, there's formulas we can use now based on the field to know, all right, we've hit an adequate depth. We've got the bearing capacity we need solely based off of the blow counts. But you need a couple pieces of information like about the hammer, the drop height, the weight, things like that. So there's a bunch of formulas to figure out this ultimate capacity. So here's that equation we talked about, the modified engineering news record formula. Well, the Danish formula, there's another formula, Wanbu. Anyway, there's lots of formulas. Like that's just geotechnical engineering formula for you. But let's just kind of look at this formula and break it apart right here. It's saying the ultimate bearing capacity of a pile is equivalent to the hammer efficiency, and then WR times H, that is the weight of the hammer. I don't know why it's not written in here. Times the height that it's being dropped, divided by, we already talked about that. We already talked about S is the blow counts, and the average penetration per blow count can be written related to the number of hammer blows per inch. So S, another way to write S is just 1 over N. That's the number of blows it takes to go 1 inch. And so that's what SC is, that modification factor. Oh, here it is. You use 0.1 if the units are in inches, and then you use 1 if the units are in SI. Okay, so then these are some new components to it. WR, that's the weight of your hammer. N squared, that's a coefficient of restitution between the ram and the pile cap. What does that mean? Coefficient of restitution is just based on when two objects collide, how much energy remains after the collision. that would have to be given to you. You'd have to understand, are you taking a steel hammer and ramming it into a concrete pile or a steel pile or a wood pile? Each type of material has a different coefficient of restitution. And then this pile, WP is the weight of the pile. WR is the weight of that hammer. And anyway, that's the equation. And if you know all these factors, and it gives you a couple of typical factors of E that you could use, the efficiency of the hammer. So some hammers are very efficient, some are not. And so they've got diesel hammers, drop hammers. Drop hammers, that's what they did in the old days. They kind of used a chain and they lowered up this heavy weight and then they dropped it and the weight, boom, fell on top of the pile. Then they raised it up again and boom. And so drop hammers, not so common. Diesel hammers, super common. And there's single and double acting hammers. I mean, there's just many different kinds of, but they're all essentially diesel hammers that drop a weight, but they just have different efficiencies. So the point is, wow, now we can go out into the field and just knowing this number, how many blows per inch, we can back calculate and figure out, if we know a lot about the hammer, wow, we can figure out our pile capacity. So this is very common for engineers after they do all their design and figure out using Terzagh's equation to figure out the bearing capacity, using the friction, figure that out. Then they still figure out the ultimate bearing capacity based off of blow counts. And then they send an EIT out into the field. So that may be one of your first jobs. And then just to count and verify, hey, these piles have reached capacity. So not only was I counting blows, I was checking to make sure that the piles were the correct batter, that they weren't tilted or leaning too much. And I was just making sure they were practicing good welding techniques as they welded on the next branch of steel, things like that. So anyway, this is a neat way to do that. Any questions about this new way to figure out bearing capacity of piles? Okay, one thing I do have, I forgot to mention at the very beginning, next semester, I will be teaching 341. That's the introduction. That's the first soil mechanics class that you've taken, a prerequisite to this class. So I'm looking for TAs. So if you need to be a TA, I'm actually looking for 2 or 3 TAs. I've got a big lab in the evenings on Tuesday and Thursday. There'll be a lot of students in it. So I'll need someone to kind of run around with me to help the different groups. Then I'll need someone to grade, and I'll need someone to help in class answer questions as a TA for homework. So, and if you're interested, email me individually. If you're sticking around next semester, and ideally, if you're even sticking around next year and you'd be back again, I need another TA for this class, but hopefully you guys will be graduated by then. Okay. Sorry, I was just looking at my notes on my board before we did this example. So, all right, how would you figure out the ultimate bearing capacity of this pile? There's 2 different ways you could figure it out. There's that modified EN formula, there's a Danish formula, there's Juan Boo's formula. But the question is, given all this information about the pile, can you find the allowable pile capacity using these 2 formulas? And so, anyway, I'm not going to really this is pretty straightforward. You can walk yourself through this. This example is exactly in the book on page, what is it? On page 610. And it's not too tricky. You just slowly kind of work your way through this. It's 12 inches by 12 inches to figure out the weight of the pile. And the cap, I think, has enough information for you to figure out all these little values in here. If you're trying to figure out, what's S? S is just going to be 1 over N, and N is just going to be, the blows for the last 1 inch of penetration. And so this 8, this has to be given to you. And this is what you kind of decide as an engineer. You'd say, when the pile is sufficiently embedded in a layer that I feel comfortable with, I want to see it take at least 8 blows for that last 1 inch to go down. And then I'll feel comfortable. And that's what you'd say. And you'd probably create a table, an Excel sheet that you'd say, okay, at 6 blows per inch, at 8 blows per inch, at 10 blows, 12. You kind of have this whole range, and it would give you a different bearing capacity, and then you just have to decide from your table and what bearing capacity you need to hold up that structure. Okay, I need 6 blows per that last inch, and then I can feel confident that I've got the bearing capacity that I need. So this 8 is probably going to be plucked off your Excel spreadsheet. But all these other values are pretty straightforward and given here. I think the trickiest one might be the, let's see. I mean, do we use 0.1 or do we use 1? Well, it's all in inches. And so in this case, we would use 0.1. But then you just plug and play. But interestingly, if you calculate all these out, you've got 101 kips, 104 kips. For the modified is 101, and the Danish brings you 104. That's amazing. It's rare that 2 equations get you that close to a value, but in this case, both formulas get you to the result that 1 pile with a factor of safety of 4 for this equation, a factor of safety of 6 for this equation, get you 100 kips. That's a lot of load. So anyway, if this is on the test, is there any confusion or questions about any parts or pieces of this equation to figure out your ultimate bearing capacity of a pile? It's kind of interesting. There's not a lot of soil characteristics that you need to know. Most equations that we've studied so far, you got to know something about the soil, like what's its friction angle or what's the cohesion. But this is like real world. You're pounding a pile into the ground, and you know the weight of that hammer, and so you're actually able to fill out bearing capacity without knowing anything about the soil. So this is neat. All right, so the next question is, how else can you drive piles in the ground? Well, you can vibrate piles in the ground, and so the amplitude can be calculated. I don't know if you understand how vibrate, but they have these 2 weights that are rotating that are that cause the vibration. They're unbalanced, and so it causes massive vibration depending on how fast they're being rotated. And then you just increase the size or the load, the static weight that's on these 2 concentrically rotating wheels, and that creates the force of vibration. So not only can you calculate the ultimate bearing capacity based on pounding a pile into the ground, you can also do it based on vibrations. But this is more used over in like Asia or Europe, not very popular in the US. Why? Because there's not as clear of an understanding between that relationship of load and rate of penetration and bearing capacity when things are vibrating. You just don't get that same good feel. However, there's an equation. If you have a vibratory type hammer, you can calculate the ultimate bearing capacity, but we're not going to really get into that. But I just want you to know this is available as well. So just if you don't have access to a driving diesel hammer and you only have vibration, you can figure it out as well. And of course, there's different folks who come up with different equations, like always. All right, but this is where I do want, this is going to be on the PE test for sure. You're going to have a question that's going to ask you, okay, great, you know how 1 pile behaves. Maybe you can figure out the ultimate bearing capacity of 1 pile based on skin friction and bearing capacity or blow counts. You'll probably have depending on what test that you take. I took the geotechnical PE exam, and so it was focused heavily on questions like this. So what happens when you have groups of piles, and how does that change the soil underneath? Does 1 pile, as you drive it into the ground, influence that 2nd pile, influence that 3rd pile? What if you had a group of 9 piles like this, 3 by 3 by 3, and you drove that 1st pile in, 2nd pile in, 3rd pile in? What's going on in the ground right here? We know that when you drive 1 pile in the ground, it has a zone of influence that goes around it. And this picture explains it. But when you drive a 2nd pile in, sometimes those zones of influence, they overlap. And so that could either be good or it could be bad. it could be good if that zone of influence is densifying the soil. Say you had a loose sand, and as you were banging that pile into the ground, it densified the soil around it as it was displacing soil. Then when you put the second pile in, it densified that overlap area even more than the first pile. Well, how could it be bad? Well, what if you were in clay, and as you were pushing this in through clay, it was stressing that clay out. And we all know that when you push on clay too much, at some point it's going to shear and slip along this sliding plane. And so too much stress in clay is bad. Clay can only handle a certain amount of bearing capacity before it fails. Terzagi's equation helps us figure those things out. And so when you drive a second pile in, what's happening is you're stressing out that clay even more than you were with a single pile. And then imagine if you were this middle pile right here, there'd be some zone of influence around all these perimeter piles affecting that zone around the clay. And so if that stress is so high that it shears, then all of a sudden you've lost capacity from this pile. It's actually not doing you any good. So there's this game that you need to play when you're putting piles in. You're trying to get efficiencies, but you don't want to overload the soil too much where you start to fail it. And so how close do you put the piles together is the question. And so what ties all these piles together is something called a pile cap, and it's just a piece of concrete, and I've got it on this next slide right here. So here's 4 different piles underneath, and then you've got one big pile cap on top. You can see there's rows and rows and rows of these. They're tied together by some braid beam. But what's important is whenever you have a group of piles, these are pretty close together. Look, I would say they're like 3 or 4 feet apart, and they've got this pile cap connecting all these different groups. Here's another picture right here. Here's 4 piles in. This pile is in at a bit of a batter, so it kind of helps it with lateral movement. But then in the end, you call this the pile cap. So going back to this, the load bearing capacity is when you have groups of piles, it's kind of complicated. They don't understand how it helps or hurts sometimes. A lot of research at BYU from the professor who teaches the foundations class there, his name is Kyle Rollins. He studies group pile capacities quite a bit, and he is granted access to these huge diesel hammers, and he conducts experiments. He puts little pile groups together, and then he presses on them with these giant hydraulic rams until failure. And so and I just think that's really interesting. So we talked about this, that stresses carried from each pile to the soil will overlap when the piles are closely spaced. And this could help and this could hurt depending on the soil conditions and how close you have these piles spaced. And so you can see your group of piles is notated as N1 by N2. So in this case, it would be 3 by 3. N1 would be 3, N2 would be 3. So if you see these values in an equation, that's what it is. And L2 or LG is the length, the total length of the pile. And BG is the total width of the pile. And if you ever have an uneven number of rows and columns, say you had four columns and you had 3 rows, well, then it would be 4 by 3. And then what one's L and what one's B? L is always the longer one. And so in this case, L would be the length of all 4 of those spaced out, and BG would be the length of the 3 rows. So anyway, we'll see these kind of notations in a minute. So I just want to make sure that's clear. So how close can you space piles? Well, typically center to center spacing D is about 2.5 D in practice. So if you're up to 3D, around 3D and more, you start losing your efficiencies if there is any when you have a group pile. But you can space them out very far. But if you space them out very far, then they start acting like individual piles. You don't get any group efficiencies if there are any. So spacing is about 3 to 5. So if you had a 2-foot diameter pile, 3D would be 6 feet. And so you'd space all these piles 6 feet apart. And efficiency, you can actually figure out if your efficiency goes up or down by having a group piles. And it pretty much, it takes all of your individual piles. Say each pile can hold 100 kips, and you had 9 piles right here. Well, it could hold 900 kips individually, right? But then what happens if as a group, if that behavior densifies the sand or something a little bit better, then it would be more than 900 kips. Those 9 piles maybe could hold 1,000,000 or 1,000, sorry. And we can figure out this value right here represents the efficiency of a group of piles. So we can calculate what that efficiency is with this kind of complicated equation, but it's not too complicated. Use those values that we just talked about. N1, that's just the number of piles that you have. So in this case, it would be 3. N2 would also be 3. And you can figure out the efficiency of your pile. P, we know what P is. That's the perimeter. L is the length. F, that's friction. We've talked about that before. So groups of piles, they can help you, they can hurt you. So how do we figure this out? Well, the approach is a 2-step approach. We have to first look at it as a giant block, and then we have to look at it individually, and we have to then take the lowest value of those two. So when it comes to group piles, the first thing you look at is like one solid giant pile that has, you know, a perimeter of BG and LG and BG and LG, and you calculate as one huge. What if that pile was just one giant pile? What would its ultimate bearing capacity be? And we're just talking about friction piles here. And when it comes to friction piles, you just have those 3 components that we talked about earlier. When I picked on, I think it was Garrett, and he said, oh, friction piles, it's the perimeter, it's the length, and it's the friction between all of those. That's all you need to know. And so when you look at this as a giant block, what's the perimeter? Well, the perimeter isn't just going to be the perimeter of this individual pile. It's the perimeter of this whole block. It's BG and it's LG. I mean, that's the giant perimeter as a block. And so what you do is you first, for friction piles, okay, well, what's the ultimate bearing capacity if I have my same average friction, and then the perimeter, this giant perimeter right here, and the length, calculate what that is. Then you do it individually. You calculate it for one pile, and then you multiply it by 9, and you figure out, all right, what do I have right here? What's better? And that will help you determine what to do, or what kind of ultimate bearing capacity to use. And you use the lower of the 2 values. Any questions about this so far? We're talking about friction piles, putting them close together, and how to figure out what the whole group is versus individually.
So if we are going to calculate just an individual pile anyways, and that's a limiting factor, then does it actually do us any good to put it in a block?
Well, what you're trying to find out, what if the block is even, okay, that's a good question. And so if the block gets worse, right? That's right. Like we were saying, so if you calculate one pile individually and it is, say, 100 kips, why would you even want to calculate the block? Because, right, if the block is better, you couldn't use it anyway. But what if the block is worse? I think that's the reason you're looking at it. And then if the block is worse, why would you use the block? Well, sometimes you have so much load that you have to, and you have it all concentrated on a certain area, you have to group all your piles together. And so you have not many other options except to put all these piles right here. I mean, you do have a couple options of picking the perimeter, the diameter of these piles and stuff like that. But some cases you need to pack a bunch of piles in an area because you have such a high load over a small location. And your goal is to figure out what the ultimate capacity could be. And you need to make sure that you take into account the block and the individual, both cases, to figure out what the lower one is, and then use that.
Okay.
That makes sense?
Yeah, so we don't use blocks because they increase our bearing capacity per se, but it spreads it over more piles.
Oh yeah, exactly right. Because in the end, you're going to put one big concrete cap over all of these. And so you're going to have one load coming onto that cap. And then that cap's going to distribute it to all 9 piles, and each of those together have a group pile capacity. Yeah, and these are pretty close together. I mean, these are maybe 6 to 10 feet apart or something like that. One thing that I need to mention, though, is when it comes to piles, how many different layers of soil is the end of the pile bearing onto?
The end only bears on one, right?
That's right. yeah, the end of the pile ends up in one soil type. There's not multiple soil types that end could be in because it's just a small area. But how many soil types could the skin friction be going through?
As many as there are.
Yeah, you could have 2 layers, you could have 20 layers. And so one thing to remember about these equations is when you're trying to sum up this F average right here, if you have multiple different layers of soil and each soil has a different friction between that steel or that concrete pile that you're putting in the ground, you need to sum them up individually. So that's just one important thing to remember. So there's a couple different equations to figure out if your piles are efficient or not. I don't know. The only thing to know about this is if this pops up on the PE test or in industry when you're working, there's just multiple equations for everything. So anyway, I'm just showing you these here so you know that there's not just one set way to figure out efficiency. But they all based off pretty much the same things. How many piles do you have? You know, how many columns, how many rows, and you can figure out the efficiency of the group or not. So let's talk about the 2 steps in figuring out the ultimate capacity of a group of piles in some clay. So here's a foundation, a concrete foundation. It looks like it's on 1, 2, 3, 4. You got 5 piles right here, all acting as a group, and it's 5 by 3. So we probably have N1 is 5, N2 is 3. And when it comes to clay, who remembers the bearing capacity, Meyerhoff's bearing capacity in clay? We talked about it last class. Does anyone remember that off the top of their head?
Wasn't it 9 times the area of the perimeter times?
Close. Speak up, Brandon.
Wasn't it 9 times the area of the perimeter times the cohesion?
Yeah, that's right. So we're talking about bearing capacity. It's 9 times the area times the cohesion of the clay. So when you're in clay, you can calculate the bearing capacity based off of Terzagh's equations. But Meyerhoff, he simplified it for us. When you're in clay, you could have QP equivalent to, and here it is, 9 times the area times CU. And so the ultimate capacity of a group of piles is you take how many you have. So in this case, we have 5 times 3, we have 15 piles, and they each have the ability to hold some load at their base, at the bearing end, tip, and then they have some skin friction. And so the ultimate of that whole group right here is going to be equivalent to this N1 times N2, which is 15 times 9 times the area times the cohesion of that clay. And then it's going to be the sum of all the different layers of soil that we have. And here, I think last time we also talked about a couple different methods to figure out friction. And we had the alpha method, the lambda method, the beta method, and Coyle and Costello's. I mean, everyone had the method. In this case right here, this is showing us the alpha method. And the alpha method simply said that friction equaled alpha times Cu. That was friction. And then of course, you're still seeing perimeter and change of length. So now, you're familiar with this. It's just friction times perimeter times length. And friction is defined a million different ways. But in this case, they're using the alpha method where you just say alpha is equivalent to, or friction equals alpha times cohesion. So step 1, this is the equation for every little pile individually. And then step 2 is look at it as a whole, as a big group. What's the ultimate capacity of the group? So you can figure them out just 15 times, whatever they can hold, and based off friction and bearing. But then when it comes to a group, we have to look at it as one giant pile with a perimeter of BG and LG going around right here. And so the skin resistance, it's going to be the perimeter, or it's going to be PG, which is the perimeter still, and times the the change in your length and then your cohesion. And so that's going to be your perimeter is just 2 times your length times 2 times your width times the cohesion times the length of your pile. And then when it comes to point bearing capacity, from Terzagh's equation, the bearing capacity of a giant pile. I mean, you have to imagine like, whoa, what if you had a footing that was this big? What if your footing was, you know, BG in width and LG in length? And you just kind of have, imagine this footing in the ground, you know, 50 feet or whatever L is, and then it has a certain bearing capacity. And that equation that we showed in the very beginning, that Terzagh's equation for bearing capacity, it had a bearing capacity factor of N sub C in it. And so there's some charts that we can use to figure that out. If we know our length to base ratio right here, LG divided by BG, we come in here. In this case, it's probably like 1.5. And then we would choose which ratio line to come up to. We kind of find that same line, 1.5, LB to LG to BG, L over BG. We come up and we come over, and our N sub C factor would be somewhere around, you know, 7.5 or something like that. So there's 2 steps. You have groups of piles. First, figure out how much load the 15 piles could hold. And then you got to figure out how much, if this was one gigantic pile, how much would that skin friction hold up with this giant perimeter? And then how much would you'd imagine that all that load being transferred down to this layer right here. And that would be your bearing capacity for your tip resistance. And you compare those two to each other, and then you see which one is lower, and that's the one that you use. So group piles, 2-step process. Any questions about that so far? The last point is just compare the values, and then, like I just said, use the lower of the 2 values as your ultimate bearing capacity. So luckily, what we keep talking about, we keep pulling on concepts that we've studied in chapter 3, and they keep coming back to us. But let's just try an example really quick. See if we can put this together. So here we've got 4 piles in the ground, and it looks like we got some clay. We have 2 layers of clay, and it looks like the end bearing would be bearing in this layer of clay, but the skin friction, we probably have to do it in 2 steps. We'd have to use this 15 feet of the pile with these cohesion and unit weight, and then this 45 feet to figure out the skin friction on this part. We'd have to use these soil properties. So that's important to know. You can't just slap one value on here. Sometimes you have to do 2 or 3 layers. So if you had a spreadsheet, you could put as many layers as you want. So we have a 3x4 group of piles. So N1 would probably be 4, N2 would probably be 3. They're square piles. This is their length. So we're able to figure out their perimeter pretty easy. So when we're trying to do friction, we need to know the perimeter, we need to know the length, and then we need to know some friction factor. Center to center spacing. All right, it tells us what D is. It's 35 inches. Ground wires at the surface. Okay, well, that makes it easy, because if we ever have to use the effective unit weight, we would know that we would just take 112 minus 62.4. And the question is, using a factor of safety of 4, what's the ultimate and allowable load bearing capacity? So the ultimate would be, what could all of this hold before the factor of safety? And then allowable is just divide that ultimate by 4, and then that's the allowable. So when you see something like this, you should think, okay, piles, it's a 2-step process. Figure them out individually. In this case, we have 12. So you'd figure out what's the bearing capacity of 1 and the skin friction of 1, multiply it by 12. That's one ultimate. And then to figure out the other ultimate, well, let's treat this like this big rectangle that it is, 3x4. It has a big perimeter. What would be the skin friction of that perimeter going through these different 2 layers of material? So that's kind of the strategy when you come up to group pile problems like this. You've just got to recognize it's a 2-step process, and you're going to choose the lower of those 2 ultimate bearing capacities that you get in the end. And then just make sure you're aware that there's 2 layers here. So I got to make sure I've got them covered. But this example is in the book. Let's see, what page is on. I think it's on page 623. it uses, I'm going to say some important equations. You need to write these down. The equations that you're going to first need is 11.121. We've covered 121 equations in chapter 11. That's pretty crazy. So to start, step one, to figure out the individual capacity of each one of these and multiply it by 12, you're going to use equation 11.121. And then for the group capacity, you're going to use equation 11.122. How many equations are in chapter 11? I'm just curious. It's up to 131. Don't think I've ever had a chapter in my school career that had 131 equations in it. So that will be your challenge on the test. As soon as you see a question, you're just like, which one of the 131 equations do I use? But the good news is it'll the questions will guide you to what to use. If it's in clay, you're like, oh, I mean, that gets rid of half the equations because half are for clay and half are for sand. So, I'm just looking at the book, just trying to point out anything that jumps out at me that's not straightforward, because the equation 11.121 is, it labels everything. It has N1, N2, it has the, we pretty much cover, there's nothing new that will jump out at you. You should be able to, when you're given an example like this, it should be quite straightforward. Yeah.
Something that I don't know, because I already started working on the homework. Where do you find the equations for LG and BG?
Okay, so LG and BG, let's go look at that. Okay, so LG and BG, so L is going to be the length of your, this is the length to the bottom of the pile. So in the problem that we were on, L would be 45 feet plus 15 feet, so that's 60 feet. But LG, that is the length of the piles spaced all out. So LG would equal, in this problem, we would take 4 times, it would be 35 inches, because that's the space between each one. Does that make sense? Let me kind of draw that line.
Yeah, I see that now.
Okay, yeah. So we know that this space in here is 35 in our problem. And so it would be 4 times 35. Let's see, actually it would be 3 times 35, because we have 4 piles in ours. 1, 2, 3. So our pile looks like this in that problem. And so to figure out LG, we would take that 35 inches. Sorry. We take this 35 inches and we multiply it by 3. Now it would give us LG. And then to find BG, right here, we just multiply that 35 inches by 2. And then we'd be able to figure out BG. And so that's what, I guess I didn't make that clear. There's 2 L's in this chart right here. LG is the length of one of your sides of your pile group. And then L is the length of your, the depth that it's embedded into the ground. So, but
Okay.
BG is the same in both of them. Good question. Any other questions? Okay, well, that pretty much wraps it up for group piles. There's still kind of a lot that we didn't get into. One thing that we didn't get into is what happens with settlement when you have a group of piles. What happens is you put some load on this pile right here, and settlement doesn't just happen like, it doesn't just pretend, oh man. So I do want to make, because I had a question like this on the PE, and it said, estimate settlement for this group of piles. And I was like, oh, I remember there's something about this. What happens is when you're a group of piles like this, and there's a load right here, you'd think, oh, well, if you had a footing, right? If I had a footing shaped like this, then the footing has it disperses the load through the soil, and then all this soil settles and consolidates, and there's equations to figure that out. Well, on a pile group like this, do we just take this area and treat it just like a footing like this and say, okay, well, here's this area of my footing and it's got some load from above, so I bet it translates its through the soil like this, and I can figure out the settlement right here. But if you think like that, you would be wrong. That is not what happens with a group of piles. Instead, what happens is, let me tell you, because I'm sure you're going to see this again. What happens is that you come down 2/3, and 1/3 from the bottom of your piles is actually where the ground starts to settle and feel the load. And so it's from this point out that you would need to calculate your settlement. So whatever load's coming down here, you would start calculating the settlement at this point, 1/3 from the bottom of your pile, 2/3 from the top, and it creates this soil pressure distribution that's going down through the soil at a 2-to-1 slope. And it's, whoa. Anyway, that's important to just know. We don't have time to cover it right now, but I did want to just bring that up and mention that's, if you read the next chapter in the book that we're not really covering about elastic settlements of group piles, you'll see that in all the pictures. There's this cone of stress that's being pushed into the soil, and it's from 1/3 from the bottom, 2/3 from the top. That's where you calculate, and that's what's going through the ground. That's how you calculate settlement from there. Because there's always two parts to the equation. We've been talking about bearing capacity. Oh, is the ground strong enough? Is the ground strong enough? Well, maybe the ground's strong enough, but it settles 4 inches. And if your client doesn't want his, air tower tank to settle 4 inches, then settlement will control. And maybe the ground could have held up that weight, but the settlement to get to that weight was just not tolerable to the client. I mean, some clients are okay with 4 inches of settlement. They just build everything and it all kind of settles 4 inches, and none of the tanks are connected to each other. So who cares if they settle? Well, sometimes they are connected with pipes and lines. And if you have a line going into a liquid nitrogen tank and it settles and breaks, that would be a problem. So we mostly cover bearing capacity in this class, and probably the test questions will focus on bearing capacity, but just know that there's settlement always in the background that may control as well. So anyway, that wraps up piles. For groups, the last 2 sections are going to be on drilled shafts. And the project that I was just on in Arizona and Texas, they had hundreds and hundreds of drilled shafts. So drilled shafts are used everywhere. People like them. You don't have to transport all these giant piles from the steel factory to where you are. You just have to have a concrete plant, and you can build a mobile concrete plant on your construction site. And then it's as simple as drilling down into the soil, filling up with concrete and rebar. That's your drilled shaft. We're going to talk about what are the differences between a drilled shaft and then driving one in a pile. Obviously, you're not able to do some of the cool things we learned about today, where you can figure out the bearing capacity just based on the blow counts per inch. That is not possible with a drilled shaft. And there's other concerns like, oh, what happens if the shaft caves in and your perfect concrete column has irregularities in it? How do we figure those out? So that's where we're going to head next Monday and Wednesday. And then we got the final on Friday. So we've got a lot coming up this next week. So email me if you got any questions, but we're getting close to the end. Thanks, everybody.
Thank you, Brother Smith.
Thank you, Brother Smith.
Thank you. Jacob, how's it going?